Okay, welcome to Lecture 8 for ECE 203. In today's lecture, we're going to look a little bit more at the Fourier series, right, and how to calculate Fourier series coefficients for a few kind of non-trivial examples. Okay, so let's just kind of go back over what we saw last lecture, and that kind of the main point of what we saw was that if x of t is a signal that's periodic with fundamental period t naught, then we can represent the signal x of t as a sum of sinusoidal functions at harmonically related frequencies. Okay, and to simplify notation, we wrote this sum as a sum of complex exponentials. Okay, so here the things I guess I want you to pay attention to are these AKs. These are the Fourier series coefficients, okay? And so in some cases there's an infinite number of these. In some cases there are only a finite number that are non-zero. But those are multiplied by this complex exponential, okay? And when we sum those up, we can get back to the signal x of t, okay? And that's for these specifically chosen complex a sub k's, which are the Fourier series coefficients, and those are given by the Fourier series, the integral equation, okay, the equation for the Fourier series coefficients. And that's just written right here, and that's just simply this 1 over t naught, so 1 over the fundamental period, which is also the fundamental frequency, times the integral from 0 to t naught, so we're integrating over one period of the signal x of t, and that's multiplied by the complex exponential with a harmonic of the fundamental frequency. Okay, so that harmonic depends on the index k, the integer k, and it's just e to the minus j 2 pi f naught kt dt. And perhaps more intuitive way to write this, but less compactly and a little tougher to deal with and analyze in practice, is what's written down here. And that's just simply as the sum of a DC component. Okay, so that's that would correspond to this little ak of a0, right? So that's just actually equal to a0, and that's written up there. And then the sum over now only the positive integers, right, of this capital AK, where capital AK is a real number, times the cosine of 2 pi f naught t plus some phase for that particular index k. Okay, so of course we could just expand this guy using Euler's identity, and then we'd realize that the lowercase a's and the capital A's are related just simply by this equation here. Okay, and that equation is I've written it for k greater than 0, and then for the negative k's, those are just equal to the complex conjugate of the positive k's. Okay, so hopefully that's clear how you can get from this equation, this one written where it's the sum of cosines, to the more compact sum all the way up top, the more compact sum of complex exponentials. Okay, so the real interpretation for this, I guess if we were to sit back and think about this, is the Fourier series analysis. The goal is to just find the best AKs and phi-Ks to represent x. Okay, and that just amounts to finding the best lowercase ak, where lowercase ak is a complex exponential. All right, so let's actually do an example. Let's walk through a simple example, and that's the square wave. Okay, so it's somewhat interesting, right? It's a little surprising that this square wave we can represent exactly with the sum of complex exponentials, sum of sinusoidal functions, right? So the square wave is defined as just taking on the value positive 1, we'll say over some duration, in particular when t is between 0 and 1, we'll say x of t has the value 1, and when x of t is between 1 and, or when t is between 1 and 2, we'll just say x of t has value 0. Okay, so that's just drawn here, right? So of course time is on this axis, right? And this is x of t. And what I have written over here, that just repeats every period, right? So let's say if this is 0, here's t naught, say that equals 2. It's periodic with fundamental period 2 seconds. Okay, after 2 seconds, the waveform repeats itself, and that's just what we're drawing here. All right, so how would I go about calculating the Fourier series coefficients? If I wanted to know what the AKs were, how would I actually evaluate these? So let me kind of just first make a brief point, and that's that this is kind of equivalent if somebody said find the spectrum of x of t. You would calculate these Fourier series coefficients. Okay, so to do that, to find the spectrum or to find the Fourier series coefficients, I would just copy that equation that we saw on the last page, right? So copy this equation and calculate the AKs. So we're just going to copy that. Remember, t naught for the square wave is 2. So that's written right here. And we get this 1/2. And now we're going to integrate over one period, right? So we're going to only integrate from here out to here, okay? And so that's, we're integrating from 0 to 2, the function x of t, now multiplied by this complex exponential at these harmonic frequencies, right? At e to the minus j 2 pi f naught kt dt. And this is a really easy integral to split up, right? It's really clear just from this definition of x of t up here that x of t is 1 from t 0 to t equals 1, and it's 0 from time equals 1 to time equals 2. So we can split up this integral over one full period into 2 separate integrals, and that's exactly what I'm doing here. So splitting it up from time equals 0 to time equals 1, and then from time equals 1 to time equals 2. And of course the second guy, right, this is just 0, because the function x of t has value 0 from 1 to 2. Okay. And again, now at this next step, we're just gonna integrate the function here, right? The function takes on the value 1, so it's 1 times this complex exponential. And let me just remind everybody that if we have an indefinite integral, e to the ct dt, right? That should just give 1 over c e to the ct, okay? And so there's nothing really mysterious that's happening with this complex number j, right? So when you see the imaginary number, it's just a constant as far as integrating goes. So I guess a lot of people seem to get tripped up on the fact that we're now doing integration with complex numbers, but just think of it as a constant, okay? So just applying this formula for the integral here, we're able to integrate this function, this expression that I have written here, right? So everything that was in the exponential, we get 1 over that. That gets written down here. And of course, this would be easy to check. If you differentiate this expression, you get back to what's inside the integral. Okay, and so this is going to be evaluated from 0 to 1. All right, so let's look at this and make sure we got this right. And you can see, right, of course, we took everything that was up here, those 2's canceled, and then the minus j pi k, that got brought downstairs, and there's a 1/2 out in front, right? We had that from before, and now we're evaluating that from 0 to 1. Okay, so that looks right. The next step is just to plug in the value 1, right? So when t equals 1, we just have this e to the minus j pi k, right? And that's actually writing that expression here. And then when t equals 0, then of course e to the 0 is just 1. So that's minus 1. And before I did that, I had factored out kind of this numerator and the numerator here and the 1/2. And just to remind everybody, if we have 1 over j, what does that equal to? Well, that's actually equal to minus j. All right? And one way to see that now is if we were to multiply the j across, then we would get j times j, which is minus 1, and negative sign of that is positive 1. But another way to see that is also remind yourself that j just equals e to the pi, or e to the j pi over 2, right? And so if we take 1 over e to the j pi over 2, that should give us e to the minus j pi over 2, which is minus j. Okay? So that, just something to keep in mind. People a lot of times just bring up the imaginary number without changing the sign of it. All right. So here's our final expression. And there's one thing that we didn't pay attention to, and that's what happens when k equals 0, right? When k equals 0, this thing is undefined because now we have this k in the denominator. So we can actually just go back up to the definition of the integral and evaluate this one for when k equals 0, and then we just get the integral of 0 to 1 of 1, and then that gets multiplied by 1/2, and it's easy to see that when k equals 0, we get 1/2. And again, to see that, go up to the definition of the integral and evaluate the integral before plugging in, evaluate the integral after plugging in the value k equals 0. Okay, and here we can see if k is an even number, just in this expression, we get, this ends up being 0, right? Because we have e to the j pi times an even number, and that's always equal to 1, right? So when that's the case, then we have 1 minus 1, and we get a 0. So anytime k is even, we have 0, and anytime it's odd, we're just left with, this ends up being a minus 1, right? We have e to the minus j pi, for example, or e to the minus j 3 pi. That's always minus 1. Okay, so that's the case, and then here I actually just brought j back downstairs to get rid of that minus sign, and we're left with 1 over j pi k for odd values of k. Okay, so the next thing I want to show is actually what happens in MATLAB when we actually start looking at expanding this square wave as sum of complex exponentials. This is sum of sinusoidal functions. Okay, so here's a little bit of MATLAB code, and really quickly what I'm doing is I'm just making a square wave, defining a square wave. That's this code up here, and then I'm plotting it in a few ways. All this for loop, let's not pay too much attention to it. That's just kind of a plotting routine. But what's happening here, I guess the interesting thing to notice is that I'm doing this sum, which is say xfs, so x created using the Fourier series, and then for kind of each value of k, I'm only going over odd values of k. I'm adding both a negative and a positive value of k, and specifically just that expression we derived, which is 1 over j pi k, right? So that's right here. And then here's the actual complex exponential part, and then also since I'm only summing over positive k, I also add a negative k, which is written right here. Okay, so that's the code, and here I can set the number of Fourier series coefficients I include in the sum. So let me run that really quick. And you're going to see a couple plots pop up, but we'll talk through each one of these. Okay, so the first one here, these are just the sinusoids that are going to be involved in creating this representation. So think of this as in the following way. So I'm going to take a bunch of sinusoids, and they're going to each have harmonic frequencies. Okay, so this is the first one I'm showing here, and I'm looking for some amplitude and some phase shift that I can apply to the sinusoid. So I'm going to multiply it by some amplitude, scale it, right? And then I'm also going to shift it in time. And I'm going to do that such that it gives me the best representation of the square wave. Okay, so that's this actually figure 2. So you can see that kind of each sinusoid, when they have increasing, the higher the frequency, the lower the amplitude, right? And that's because we had an expression that was like 1 over k, right, where k was the index of the sinusoid. So here's the first one. Remember, actually the second, the even one is 0, so I didn't show that. The third one then has like an amplitude 1/3, and so on. And the fifth one would have an amplitude actually like 1/2 times 1/5, and you would get that here. Okay, so, and you can see each one of these has a different phase. So what does the resulting plot look like? Well, that's shown here. In blue I have the original square wave, okay, and in red is my Fourier series representation. So this is only using now 10 complex exponentials, and you can see that it's close, but we still have this, if I zoom in, and it should be obvious right away, that we still have this kind of wild variation right around these sharp corners of the square wave. Okay, so in order to exactly represent that for the square wave, we actually need an infinite number of sinusoids. But let's go back to the code and let's just crank up that number to 10 to 100, for example, 100 sinusoids, and it's going to create a couple figures. And you can see now that we have this red representation is much closer to the original square wave. So let me zoom in on this, and we can see again now these oscillations appear much more rapidly, but we can see that kind of on average we're substantially closer. So now again, let me increase this to even more, and should see that now we're essentially with 1,000 complex exponentials, right? So it's actually 500 sinusoids. We're really close. Okay, but we still kind of have these rapid oscillations around the square wave. And those are often referred to as something called Gibbs phenomena. Right. So in order to make those entirely go away, we would have to, of course, take an infinite number of sinusoids in our Fourier series representation. All right, so really quickly down in the corner here, I just want to maybe draw the spectrum of what this signal would look like, right? So forgive me because there's not a lot of space, but hopefully you guys will be able to get the idea. So the first thing I would say is that we'd have this DC component, right? And that's just going to be the value when k equals 0, okay? So at frequency 0, we'd have some component that has amplitude 1/2, right? And when k is even, we actually have amplitude 0. So we'll only really need to plot the odd values of k. All right. And so for k equals 1, that corresponds to a frequency of 1/2, right? Because that's the fundamental frequency. So we'd have some frequency here that would be, so let's just say 1/2 is right there, and we have amplitude here would be 1 over pi j, right? Right, and that's at 1/2 a hertz. And then of course we also have the same thing at the negative component is really just 1 over minus 1 over, well, let's actually write that differently. Let's just write that as the complex conjugate, make that clear, so it's 1 over minus j pi, and that's at a frequency of minus 1/2, right? And then so for k equals 2, there's nothing there, right? So that's at a frequency of 1. For k equals 3, then it should be at minus 3/2 and plus 3/2. Okay, so minus 3/2 and plus 3/2. And we should have amplitude of this is, or the number I'm going to write next to this thing, which should be getting smaller, right, is it's just going to be 1 over j 3 pi, right? And then down by the -1, it's going to be the same. It's going to be 1 over minus j 3 pi. Okay, so this is how I would draw the spectrum of, this is how we would come up with the spectrum of the square wave. And then we denote more dots here to show that these actually continue on, that there's an infinite number of frequency components. Okay. All right, so the next thing I want to, I guess, talk about again is just this concept of how the Fourier series, a good way to think of them is by imagining these harmonic sinusoids as being the basic building blocks. Okay, and our goal in finding the Fourier series coefficients, right, is to find an amplitude and a phase for each one of these sinusoids. So these are, this picture again is what we saw before. It goes with the square wave. But the goal is to multiply each one of these sinusoids, like I said, by some amplitude and then shift its phase so that it matches x of t as closely as possible, right? And if we do that for all of these harmonic frequencies, right, if we, here's the DC one, if we multiply that by some, what's normally just called A0, right? And if we multiply this guy by some A1, and then we give it some phase shift, and then multiply this next one, so find some A1 and some Phi1 for this guy. In the square wave, the even ones were not present, so this one's actually A3, right? A2 was 0, and so phase didn't matter in that case. And then we'd also have some phase shift for A3, and so on. And then at the end of the day, these would all get added up, and that would give us back x of t. Okay. So the idea is these sinusoids are somehow basic building blocks. We're giving them some amplitude and some phase shift so that they fit the signal x of t as good as possible. And then on the next screen is just what I'm showing essentially now. The same plot on the left here that we saw on the last screen, but on the right now is the sinusoids, the same sinusoids on the left except scaled by the amplitude and phase required to represent the square wave. So we just saw this, right? And the complex amplitude AK is like 1 over j pi k. Okay, and that's only for odd values of k. And when we did this, when we added those first 6 sinusoids up, right, we actually got this red wave, which we saw. So it's close, but using only 6 sinusoids to represent this square wave that has these step discontinuities in them, isn't that great? And you get these kind of these little towards the discontinuities, we get these oscillations. Okay. All right. Okay, so like I said, we can think of each Fourier series coefficient as kind of being the best fit of this complex exponential to the sinusoid x of t, right? And so I guess to be a little more mathematically precise, we're going to try and run through some analysis quickly here, and that'll be the last thing that we'll look at today. But by best, when we say we want to find the best fit, we could mean a number of things. But in this case, one thing we actually mean precisely is that the mean squared error is minimized. if I define the error of A to be as follows, okay? So if I define it to be as we have written in this equation that's underlined in red, so it's a fair amount to look at, but if I say just let A be any complex number, right? And I'm trying to make this complex exponential fit as close as possible to the signal x of t. How good of a job is this particular A doing? Well, one way to quantify that would be to basically, let's look at, say we have some x of t, right? I have x of t, and it has some, maybe some oscillation like that. And let's just also say that there's some complex exponential that happens to have, let's say, maybe something, a signal like that. And then when I say a complex A, let's say if I shift this complex exponential that I drew, the black one, it looks like it would somehow fit the original signal better, right? And so one measure of that is we can just take the integral of the difference between the two signals, right? So one signal being the original signal x of t, and the other signal being the complex exponential with some amplitude and phase scaled by this complex number. Okay, and we'll show that the best value of A that we could put in here, the one that minimizes this error, is actually the equation for the Fourier series coefficient. Okay, right, which is very intuitive in that it tells us that the A that minimizes the mean squared error is exactly what we're calculating for the Fourier series coefficient. Okay, so how do we do that? Well, again, we're going to start with this expression here for the error, and that's just rewritten here, and we'll try and walk through this analysis. So when I have the absolute value of a complex quantity squared, I can just write that as, well, before I do that, say the first thing that I'm going to do is I'm going to actually add and subtract. So this won't change the value, right, of what's in this integral if I add and subtract ak e to the j 2 pi f naught kt. I'm just going to add and subtract that. And the reason I'm going to do that is we'll see in a second that's going to greatly simplify things. And really the reason I do that is because I know how this proof progresses. Right? It might seem like a strange thing to do. It's kind of a first step. But of course you can always add and subtract the same number to anything and it doesn't change the value. Right? Okay, so I'm adding and subtracting ak e to the j 2 pi f naught kt. And then I'm actually just going to expand. Now we have this four-term thing. There's 1, 2, 3, 4 terms. The absolute value of 4 terms and that quantity squared. Right? And so I can always write the absolute value. So this whole thing, it's 4 terms, but just think of it as a complex number. So I can always write the absolute value of a complex number squared as just being equal to A times A conjugate. Right? And that's just a definition. So a complex number, absolute value squared, I could write as A times A conjugate. So imagine now this whole number that is comprised of 4 terms, I'm writing as A times A conjugate. Right? And that is actually, when I do that, then I see I end up with a number of things. Okay, so again, I remind everybody, if I were to take a few more steps in doing this, I would write out this line, the things I just put in parentheses, and then multiply that by its own conjugate. Okay, and what I would see is I'd get, these first 2 terms, they would be multiplied. One would be multiplied by the conjugate of the other, And that actually is just equal to the absolute value of that number, right? By the reasoning that we just saw, this definition that absolute value is A times A conjugate, right? So this next line is going to hold with the equality, and this first term comes from these guys, okay? That guy gets multiplied by his own conjugate, and that gives this term. And then also we have another term, which is these guys. That gets multiplied by its own conjugate, okay? And that gives this term, okay? And then there's of course these cross terms, like, right, if we wrote all this out, we'd have this times this, and then this times this, right? Each time one is conjugated, the other is not. And those are these ensuing two bottom terms, okay? All right, so let me now erase kind of all these notes, circles that I've put on here, these unnecessary circles. Okay, and now when we look at this last bunch of equations, right, the first two terms are always positive. And the reason that is because, of course, we're taking the integral of a function that's always positive. So we have the integral of something that's always positive, that's always greater than 0. And that's true for the first and the second term, right? And in particular, the first term is actually equal to the error if we set A to be A sub k, right? Just that's the way we've defined this, right? This is exactly equal to the error of AK. And so the second term, it's also easy to see that actually equals 0 if and only if A equals AK. So this integral, since we're taking the absolute value here, right, the only way that this integral can be equal to 0 is if A is equal to AK. If A is equal to AK, the whole thing cancels. If not, there's always some value, and we're integrating a strictly positive number, and it's greater than 0. Okay, so on the next page, we're just going to show that these second two terms, this one and this one, are equal to 0. Okay. All right, so let's continue and do that. Well, I'm just copying over, only taking the third term here just to walk through that one, and we'll see the fourth term is very similar. And we're going to show that this is actually equal to 0. There's a number of steps here, and the first one, I'm just rewriting things, and then I'm just going to start multiplying things out. Okay, and you'll see in the first one I get an x of t times ak times, or ak conjugate minus a conjugate times a complex exponential. That's the first integral. And then of course I can bring outside of that, I can just pull the ak conjugate minus ak outside, and I'm just left with this integral, and that's actually that's just T naught times the Fourier series coefficient, right? That's T naught times AK. So that's actually, I'm writing that down here. So that term. All right, and then the second term that we get now from multiplying this guy times this term is written right here, and we can see two things happen right away. This and this cancel, right? And we're just left with this integral over 1 from 0 to T naught, and sure enough, it's underlined here. These quantities are identically equal. Okay, so those two things cancel, and we've just shown now, if I go back, that this third term, that's actually equal to 0. So that's gone. Now, the same way we could show this fourth term is equal to 0. All right, so we're left with, really, like we said before, these two first terms. The first one is identically equal to the error of AK. It's just by definition. And the second one is 0 if and only if A equals AK. So what does that mean? That means if we use any other definition for A, if we pick any other value for A, it's going to have larger error than if we used AK, right? So to rewrite these four things, which I have written here, the error of A, like I said, again, is now equal to the error of AK plus some positive number plus 0 plus 0. And that positive number, right, is equal to 0 if A equals AK, just to kind of restate myself. And we think about this and we pretty quickly can conclude that the error of choosing any other number, any other complex number A, is going to be greater than AK, right? So that really just implies that in choosing AK to be the integral, this integral here, is the quote-unquote best choice in terms of minimizing the mean squared error. Okay, so let's say a few quick things. I just want to mention orthogonality, and this is kind of a general principle that comes up in linear algebra and in different places in signal processing. And really what the property that these harmonic complex exponentials have that make them so appealing is that they're orthogonal. And what orthogonal means, is we actually evaluated this integral last time, is that when we integrate one times the other, it either gives us 0 or some positive value. And it gives us 0 if these complex exponentials have different integers k and m. Right? If k is not equal to m, it's just equal to 0. And if k equals m, then we get some positive number. And because of this property, we can carry out this fitting of these different sinusoidal building blocks to the signal independently. Okay, we can do it independently. It doesn't have to be an optimization simultaneously. We just have one equation to give us each AK. So to summarize what we've seen about the Fourier series, it's been a lot in the last two lectures, but what we can say is that any periodic signal can be represented by a sum of harmonic sinusoids. Right? In particular, we can write the following. We can write x of t is the sum of complex number times the complex exponential at a harmonic frequency. Right? And these Fourier series coefficients, the AKs that show up in this equation, are just given by this integral equation. And in some sense, the Fourier series coefficients optimize the fit of each harmonically related sinusoid to the signal x of t.